The diagram at the bottom shows our experiment setup. We measured the net force of the IOLab as we pulled it. The force we applied to pull the IOLab was kept constant by keeping the weight at the end of the string the same in every trial. We only changed the surface that the IOLab was pulled across to see if the change in friction changed the amount of work we needed to move the IOLab. We first pulled it across the table in the physics room, then across some sandpaper and across a square carpet we put on the table. Here we show 4 free body diagrams. The first one is when the IOLab is being pulled, but there is not enough applied force to overcome the friction force, which is why it shows that the forces are equal and opposite. The next diagram is when the IOLab is moving across the table. There was very little friction, which is why the applied force is shown to be so much greater than the friction force. The next diagram shows that sandpaper has a greater friction force than the other surfaces. The net force here is closer to 0 than it is on the other surfaces, which we saw in our results. The kinetic friction force calculated in the carpet and table trials was similar, which is why the free body diagrams for those surfaces look the same. The equations at the bottom were used to calculate the friction force and the work done by friction. These are the results for the first trial on the table. There's static friction acting on the IOLab from about 4 seconds to 5 seconds. The peak of the static friction force is where the net force is highest, which is seen at a little past 5 seconds. Then kinetic friction acts on the IOLab from 5.5 seconds to the end. The results from the other 2 trials on this surface are very similar to this one.
The average net force during static friction and the average net force during kinetic friction for each trial were used to calculate the static and kinetic friction forces and their static and kinetic coefficients of friction. Our FNet equation was Fnet equals force applied minus force of friction. To find the static friction force for trial 1, we used the Fnet equation and plugged in the average net force during static friction and applied force, which is 2.646 newtons, to solve for the static friction force. The static friction force for trial 1 was found to be 1.718 newtons and was then used to solve for the static coefficient of friction. The static friction force and the force normal acting on the IOLab, which is 2.0727 newtons, were then used to solve for it. The static coefficient of friction was found to be 0.828, which is a unitless number. The methods used to find the kinetic force of friction and kinetic coefficient of friction were similar to the ones used for static friction. The kinetic force of friction was found to be 1.338 newtons. The kinetic coefficient of friction was found to be 0.646. This proves that the kinetic coefficient of friction is lower than the static coefficient of friction. The force of kinetic friction was then used to find the work done by friction over a distance of 0.28 meters. The work was found to be 0.3647 joules of energy.
The first trial of sandpaper, static friction was acting on the IOLab during the time interval of around 0.57 seconds to 0.77 seconds. Force dips below 0 newtons momentarily during this interval, and we attributed this to an error of the force sensor on the IOLab. The kinetic friction was acting on the object during the time interval of around 0.78 seconds to 0.99 seconds. The other trials look similar to this trial, though the force did not dip below 0 newtons.
The methods used to find the static and kinetic forces of friction and the static and kinetic coefficients of friction were similar to those used to find those values for the table. The static force of friction for trial 1 on sandpaper was found to be 2.4669 newtons. The static coefficient for sandpaper, trial 1, was found to be 1.1902. The kinetic force of friction for trial 1 on sandpaper was found to be 1.9160 newtons, and the kinetic coefficient was found to be 0.9242. The work done by friction was found to be 0.5365 joules of energy.
These are the results for the first trial on carpet. There's static friction acting on the IOLab from 4 seconds to 5 seconds. The peak of the static friction force is where the net force is highest, which is at about 5 seconds. Then kinetic friction acts on the IOLab from about 5.5 seconds till the end. The results from the other 2 trials on the surface are very similar.
The methods used to find the static and kinetic forces of friction and the static and kinetic coefficients of friction were similar to those used to find those values for the table and for the sandpaper. The static force of friction for trial 1 on carpet was found to be 1.847 newtons. The static coefficient for carpet trial 1 was found to be 0.891. The kinetic force of friction for trial 1 on carpet was found to be 1.448 newton, and the kinetic coefficient was found to be 0.699. The work done by friction was found to be 0.40544 joules of energy. The average force of kinetic friction, work done by friction, static friction coefficient, and kinetic friction coefficient for each surface was found. It can be seen that sandpaper has the highest average for each of those values. It can also be seen that those values for the table and carpet are very close together, showing that even though there are different surfaces, the work done by friction on each of those 2 surfaces is similar. A histogram of the force of kinetic friction was made for each surface to visually show the average value of the force of kinetic friction on each surface. If you look at where the peak of the bell curve is, you can see what the average kinetic friction force of that surface is. By looking at these results, it can be seen that the energy required to move an object across the surface with higher coefficients of friction is higher than the energy required to move the same object over a surface with lower coefficients of friction.
In conclusion, we found that the work done by friction is the highest on the sandpaper, followed by the table, then the carpet. These results support our hypothesis that surfaces with higher friction coefficients would result in more work being done by friction when moving an object a set distance. During the experiment, we also made other observations. One of these observations was that the static friction coefficient was on average higher than the kinetic friction coefficient. Another observation was that the carpet's static friction coefficient was significantly higher than the table's static friction coefficient, but the kinetic friction coefficients were very similar.